In November 2023, a quiet deadline changed how independent Mac software could pass through Apple's security machinery. Apple's notarization service stopped accepting uploads from the old All-Tool workflow and pushed developers onto Notary Tool and newer Xcode releases. For most users, nothing dramatic happened. Apps still opened, downloads still installed. The desktop looked exactly the same, but for developers shipping outside the Mac App Store, the message was unmistakable. Distribution now depended on an increasingly formal trust chain. The app had to be signed correctly, built with the hardened runtime, submitted to Apple, scanned, accepted, and packaged so Gatekeeper would trust it. This was not app review. Apple was not judging the business model, interface, or usefulness of the software. It was an automated security process designed to detect malicious components and verify that the code had been signed in an acceptable way. And yet, that distinction did not erase the deeper tension. Apple still sat between the developer and the user at a critical point in distribution. For a growing class of engineers, that tension reaches far beyond one upload command. It appears in entitlements, sandbox boundaries, protected system directories, driver frameworks, privacy permissions, and the shrinking space for kernel-level modification. The Mac remains one of the most polished developer machines ever built. Apple Silicon is fast, quiet, power-efficient, and tightly integrated with the operating system. Xcode remains mandatory for building Apple platform software, and macOS still offers a Unix foundation beneath a highly refined commercial desktop. So the real story is not that developers suddenly discovered Linux and abandoned the Mac overnight. No credible industry dataset shows a mass flight from macOS. The change is narrower, more technical, and potentially more important. Developers whose work depends on deep system access, Linux native production environments, container infrastructure, security tooling, or GPU compute are facing a different calculation. They are asking whether a machine can still be considered a developer's machine when the owner does not control every layer of the stack. And that question exposes the hidden cost of Apple's garden. For years, the Mac occupied an unusual position in software culture. It gave developers a commercial desktop with a Unix command line, mainstream creative applications, excellent laptop hardware, and access to Apple's mobile ecosystem. A programmer could spend the morning inside a shell, the afternoon in a browser or a design tool, and the evening compiling an iPhone app on the same machine. That combination mattered because traditional Linux desktops often demanded compromises in commercial software, laptop hardware, battery tuning, peripheral support, or corporate management. Windows had enormous application compatibility, but before modern Linux integration, it did not feel as naturally aligned with Unix-centric web and server development. The Mac sat in the middle, consumer polish above, Unix conventions below. Then the modern security model hardened. Apple introduced System Integrity Protection, or SIP, years before the current debate. SIP limits even the root account from modifying protected portions of macOS. Directories such as System, Bin, SBN, and important parts of USR are protected because Apple does not want malware or an administrator making a catastrophic mistake to casually rewrite the operating system underneath a running Mac. On Apple Silicon, those protections sit beside additional hardware-backed mechanisms intended to protect the kernel and boot process. From Apple's perspective, this is not hostility toward developers. It is the logical result of designing a computer whose security should not collapse merely because one process gains administrator privileges. That philosophy is defensible. It is also fundamentally different from the philosophy many systems programmers associate with a general-purpose Unix workstation. On a conventional Linux installation, an administrator can usually replace the kernel, rebuild it, load supported modules, change security frameworks, alter boot parameters, swap entire userlands, or install a different distribution. The machine may warn you, it may break, but the system generally treats that risk as yours. Apple increasingly treats some categories of risk as architectural decisions the platform should prevent by default. The difference looks small when writing JavaScript. It becomes enormous when writing a driver, endpoint security product, low-level debugger, hypervisor, file system utility, network filter, or anything else that lives close to the operating system boundary. Kernel extensions show the transition clearly. For years, developers could extend macOS through key XTs that ran inside the kernel. Kernel code is powerful because it can interact with hardware and core operating system services at the deepest level. It is also dangerous. One faulty driver can destabilize the system. One malicious extension can acquire extraordinary privileges. Apple began deprecating broad classes of kernel extensions and moved developers toward system extensions and driver kit. These newer components run in user space and communicate with the kernel through controlled interfaces. Network extension handles many networking use cases. Endpoint security provides sanctioned access to security events. Driver kit handles categories of hardware that once required kernel-resident code. The security logic is strong. If a driver crashes in user space, the entire kernel is less likely to go down with it. If a security tool needs to inspect process events, Apple can expose a defined API instead of giving arbitrary third-party code a permanent seat inside the kernel. Users gain stability, and Apple can evolve the operating system without supporting an unlimited collection of private kernel assumptions. But the bargain has a price. A developer can only do what the exposed framework permits. When a low-level capability has no supported equivalent, the engineer cannot simply treat the kernel as an open laboratory. Apple's own documentation tells developers to prefer system extensions and driver kit, and modern macOS releases refuse some kernel extension approaches when an equivalent system extension path exists. That is the wall developers actually encounter. It is not a literal ban on programming. It is the conversion of formerly open-ended privilege into specific brokered capabilities. App Sandbox reveals the same philosophy at application level. For software distributed through the Mac App Store, sandboxing is required. A sandboxed application begins with sharply limited access and declares specific capabilities through entitlements. File access, network behavior, hardware features, and other resources are mediated rather than assumed. Again, the purpose is security. If an image editor is compromised, the attacker should not automatically inherit permission to rummage through unrelated documents, listen to arbitrary network traffic, or modify system resources. The application receives the smallest useful set of privileges. For a traditional consumer app, this can be excellent engineering. For a tool whose job is to interact broadly with the machine, the constraints can become design-defining. Backup utilities, developer tools, automation software, virtualization products, security agents, debuggers, and system management tools often exist precisely because they need to cross boundaries normal apps should never cross. Apple does provide ways to handle many of those cases. Some software can ask users to select files. Some can request specific entitlements. Full disk access can be granted manually by the user for workflows that genuinely need it. System extensions can receive elevated capabilities through approved frameworks. Distribution can also occur outside the Mac App Store, where App Sandbox is recommended rather than universally required. That last detail matters because it destroys the most sensational version of the story. Apple has not made every Mac application live inside the App Store. Independent Mac developers can still distribute software directly. Developer ID signing and notarization are the normal path for making those downloads pass Gatekeeper cleanly. But direct distribution is no longer synonymous with an unmanaged executable. A professional developer shipping a normal Mac app outside the store still has to think about code signing, hardened runtime rules, notarization, gatekeeper behavior, privacy prompts, entitlements, and the possibility that a future macOS release changes an interface that used to work. For Apple, these are layers of defense. For some developers, they are layers of negotiation. Notarization is the most visible example because it inserts Apple's infrastructure into a release pipeline. A developer ID-signed application is submitted to Apple's notary service. The service scans it for malicious content and code signing problems. If accepted, a ticket can be stapled to the software, and Gatekeeper can use that trust information when the user opens it. That is far less restrictive than App Store review, but it creates a dependency. Release engineering now includes a remote service controlled by the operating system vendor. If notarization is delayed, unavailable, or rejects a build because of a signing mistake, a developer may not be able to ship the clean user experience they expected at that moment. The objection is not that malware scanning is irrational. The objection is architectural. The developer no longer controls the entire path from source code to executable to user. Linux reverses that relationship. There is no single Linux corporation that owns the kernel, the desktop, every distribution, the package ecosystem, and the signing authority. The kernel is developed through an open contribution process, and code entering mainline must use GPL-compatible licensing. Distributions can impose their own signing and packaging rules, but no universal Linux gatekeeper decides whether a compiled program is acceptable to every Linux user. That freedom is messy. A developer can distribute a binary archive, maintain a repository, publish a container, build a Flatpak, use a distribution package, ship source code, or ask users to compile the software themselves. Those options fragment the ecosystem, but they also mean a single vendor rarely controls the entire route. For engineers building infrastructure, the difference is even stronger. Linux exposes extensive user space APIs for namespaces, networking, file systems, security modules, eBPF, performance tracing, virtualization, device management, and process isolation. If the exposed interface is insufficient, developers can inspect the kernel source, patch it, build their own version, or propose a change upstream. That does not mean Linux accepts anything. The kernel community has maintainers, review standards, subsystem policies, licensing requirements, and a reputation for demanding technical discussion. Getting a patch into mainline can be difficult, but the argument happens around source code and technical review. rather than a proprietary entitlement that only one platform owner can grant. For certain engineers, that difference is intoxicating. A Linux workstation can be transformed into the thing being developed. The operating system is not merely the host for the experiment. It can become part of the experiment. This matters most in fields where production is already Linux. Cloud servers overwhelmingly run Linux-based operating systems. Containers commonly package Linux user space. Kubernetes nodes are usually Linux. Many backend services, data systems, networking stacks, observability tools, and security platforms ultimately execute on Linux, even when their developers use Macs. For years, the Mac's Unix-like environment made that difference easy to tolerate. A shell felt familiar. Package managers supplied familiar tools. Containers and virtual machines hid the kernel mismatch. A developer could code on Mac OS and deploy to Linux without thinking deeply about where one operating system ended and the other began. Containers complicated that illusion. Linux containers rely on Linux kernel primitives. On a Mac, a Docker-style Linux container cannot simply share the Mac OS XNU kernel as though it were Linux. A Linux virtual machine sits underneath the container environment, whether the abstraction is obvious or hidden behind polished tooling. For most application developers, that arrangement works brilliantly. For low-level networking, file system behavior, performance analysis, eBPF, kernel modules, GPU access, or production debugging, the abstraction can become friction. The closer the application gets to Linux itself, the more useful it becomes to develop on Linux itself. That trend has strengthened as containerized and cloud-native workflows have become ordinary rather than specialized. Stack Overflow's 2025 developer survey described Docker as effectively near universal in modern cloud development and reported a striking jump in use after its survey categories were consolidated. The desktop operating system became less important for some programming tasks, while the production kernel became more important. Artificial intelligence adds another pressure point. Apple Silicon has impressive integrated GPUs and increasingly capable machine learning frameworks. Apple supports Metal, Core ML, and newer developer tooling designed around its hardware. For local inference and Apple-focused software, that ecosystem can be excellent. But much of high-end AI training and research still revolves around NVIDIA, GPUs, and CUDA-based software stacks. Linux is the dominant environment for many multi-GPU servers, research clusters, inference fleets, and cloud accelerators. An engineer working on those systems may use a Mac as a terminal, but a Linux workstation can reduce the distance between local experimentation and production behavior. The same logic appears in cybersecurity. Apple's endpoint security framework gives approved software a structured way to observe important events, such as process execution and file system activity. That is powerful. Yet security researchers often value the ability to instrument, trace, alter, and sometimes intentionally destabilize the operating system beneath them. Linux offers that possibility at almost every layer. Developers can rebuild kernels with debugging features, use eBPF, inspect namespaces, change mandatory access control policies, experiment with file systems, load custom modules where policy permits, and reproduce server environments without translating behavior through a proprietary desktop abstraction. That freedom has a downside. It also gives users more ways to weaken security or destroy a working installation. Apple's model reduces entire classes of accidents by making certain modifications difficult or impossible in normal operation. Linux generally assumes that a sufficiently privileged administrator may choose a dangerous configuration. The debate, therefore, is not freedom versus oppression. It is control versus managed safety, and both sides have real costs. Apple's approach has produced tangible benefits. Malware cannot simply assume that root means unrestricted access to every protected operating system component. Sensitive user data is guarded by privacy controls. System extensions reduce kernel attack surface. Code signing and notarization make it easier for Gatekeeper to distinguish software from identified developers and detect known malicious content. The Mac also gives developers something Linux often cannot match in one standardized package: tightly integrated hardware, consistent sleep behavior, excellent displays, strong battery life, high-performance media engines, mature commercial creative software, and access to every Apple development framework. Those advantages are why any claim of a wholesale developer exodus immediately fails the evidence test. If developers were broadly abandoning macOS, major surveys should show an unmistakable collapse in professional use. They do not. The 2025 Stack Overflow survey still treated macOS as one of the normal primary operating systems developers work on, alongside Windows, Ubuntu, other Linux distributions, and mobile platforms. Tens of thousands of respondents described a mixed environment, not a stampede away from Apple. The more accurate pattern is specialization. Developers are becoming more willing to choose the operating system that matches the layer they actually control. An iOS engineer has little reason to flee. Xcode, Apple simulators, signing, deployment, and platform SDKs still anchor that work to the Mac. A designer-developer hybrid may prefer macOS because the same machine runs professional creative suites and Unix tooling. A web developer may barely care what host OS is underneath a browser, editor, and container runtime. A kernel engineer, cloud infrastructure developer, self-hosting enthusiast, security researcher, or CUDA heavy machine learning engineer may care intensely. For them, the Mac can feel less like Unix with a beautiful interface and more like an appliance that happens to contain a Unix command line. The Apple Silicon transition sharpened that feeling in unexpected ways. Moving away from Intel gave Apple enormous control over performance, energy efficiency, secure boot, memory architecture, and hardware-software integration. It also made the Mac less generic. The machine is no longer simply an industry-standard x86 computer running Apple's operating system. It is an Apple-designed computing platform from processor to boot chain to desktop. That integration is the source of the Mac's greatest strengths. It is also the source of its deepest lock-in. A developer dissatisfied with a Linux distribution can install another one on compatible hardware, replace the desktop environment, swap package managers through containers, compile a kernel, or buy a different vendor's machine while preserving much of the software stack. On modern Apple hardware, macOS and Apple Silicon are designed as one product. Alternative operating system efforts exist, but Apple does not sell the Mac as a neutral PC whose intended purpose is arbitrary operating system replacement. The result is a philosophical divide over ownership. Apple defines the product as an integrated platform whose integrity depends on limiting what software can do by default. Many Linux developers define a computer as a programmable machine whose owner should be the final authority, even when that authority is dangerous. Apple fears the failure where malicious or buggy software compromises a user's machine because the operating system granted too much privilege. Linux culture often fears the failure where a platform owner prevents legitimate experimentation because the operating system grants too little autonomy. The conflict becomes visible whenever Apple closes an old mechanism and replaces it with a newer framework. Kexts become system extensions. Unrestricted file system assumptions become privacy prompts. Unsigned distribution becomes signed and notarized distribution. Private tricks break as internal APIs change. Each step can be justified individually. Taken together, they form a directional trend. The Mac is becoming more explicit about which kinds of extension are legitimate. That is the hidden wall. It is not a single policy document. It is the accumulation of boundaries. A developer may accept every one of those boundaries and still eventually notice that the machine is asking permission from Apple's architecture more often than the developer's architecture is asking permission from the machine. At that point, Linux becomes attractive not because it is easier, but because it is negotiable. If the desktop environment is wrong, replace it. If the kernel lacks a feature, patch it. If the distribution chooses a package format you dislike, use another distribution. If the security policy is too permissive, harden it. If it is too strict, alter it. That range of choice can waste enormous time, but it also lets advanced users align the system around a specialized workflow instead of aligning the workflow around the platform. A switch from Mac to Linux can therefore exchange one category of friction for another. The developer escapes notarization and platform entitlements, then spends hours debugging suspend behavior, fractional scaling, a proprietary driver, a security token, or a vendor application that officially supports only Windows and Mac OS. There is no universal liberation machine. What has changed is the threshold at which those Linux costs become worth paying. For infrastructure engineers, that threshold drops because their servers are already Linux. For AI researchers, it drops when local NVIDIA hardware matters. For security developers, it drops when kernel observability matters. For privacy-focused engineers, it drops when they want the operating system itself to be inspectable and replaceable. For open source contributors, it drops when their target platform is already the Linux desktop or kernel. Meanwhile, Apple keeps improving the opposite proposition. The company is betting that most developers will value a secure, predictable, vertically integrated workstation more than unrestricted control over the operating system's deepest layers. That bet may be correct for the majority, but software innovation often begins with minorities who need capabilities that mainstream platforms do not yet consider safe, profitable, or important. Containers began as obscure kernel primitives. Modern observability depends on capabilities once used mainly by system specialists. Virtualization, packet filtering, custom file systems, tracing, and accelerator programming, all reward environments where developers can reach below ordinary application boundaries. When the next category of software emerges, the question is not merely whether macOS has an API for it. The question is, who gets to decide what happens before the API exists? On Linux, a determined developer can prototype inside the kernel, build a module, create a user space interface, publish the source, and attempt to persuade maintainers that the mechanism belongs upstream. The community can reject the patch, but the experiment still existed on the developer's machine. On macOS, the equivalent experiment may collide with a protected subsystem, a missing entitlement, an unavailable kernel interface, or a framework whose supported behavior stops before the experiment begins. Apple can later expose a sanctioned API, but until then, the platform's security boundary may be the end of the road. That is the innovation argument at the heart of the dispute. Security frameworks protect millions of users from software they should never have trusted. The same frameworks can prevent a tiny number of expert developers from doing something genuinely new at the same layer. There is no simple technical formula that determines the correct balance. And the balance changes as computers become more personal. A modern laptop holds passkeys, financial sessions, private messages, health information, source code, company credentials, photographs, and authentication tokens. The cost of allowing arbitrary low-level software to compromise it is far higher than it was when hobbyist Unix workstations lived on isolated networks. Apple is designing for that reality. Linux is adapting too. Secure boot, sandboxing, mandatory access controls, immutable distributions, signed repositories, flatpak permissions, container isolation, and memory-safe components all show that Linux is not frozen in an era of unrestricted root access. The difference is that these controls generally emerge from multiple projects rather than one company defining the entire platform boundary. Ironically, the two worlds are converging technologically while diverging politically. Linux desktops are borrowing stronger application isolation and immutable system ideas. Apple is exposing safer user space replacements for functions that once required kernel access. Both ecosystems are trying to preserve power without allowing every program unlimited authority. The disagreement is about who controls the escape hatch. That brings us back to the supposed developer exodus. The dramatic phrase is useful only if we define it correctly. There's no verified mass evacuation of Mac developers. There is a migration of particular workflows and a growing willingness among technically demanding users to separate their personal desktop from their development target. Some keep a MacBook and SSH into Linux workstations. Some run Linux VMs. Some move their primary machine to Linux but retain a Mac for Apple platform builds. Some use macOS for general work and remote Linux for AI or infrastructure. The modern developer desk is becoming heterogeneous rather than ideologically pure. That may be more threatening to Apple than a headline about people throwing away MacBooks. The Mac's historical advantage was that it could be the one machine that satisfied nearly every developer need. If developers increasingly treat it as one client among several environments, Apple still sells excellent hardware, but macOS loses some of its position as the natural center of technical work. Once that happens, switching the local desktop becomes easier. A programmer whose identity is tied to Xcode is tied to macOS. A programmer whose environment is defined by a container image, dot files, NeoVim or VS Code configuration, remote build host, and language package manager can move between operating systems with far less pain. This is why platform control can produce an unintended consequence. Every restriction that encourages developers to move important work into portable environments also reduces the strategic importance of the host platform. Apple's garden can become so well managed that the most experimental plants are grown somewhere else. The final irony is that macOS itself descends from Unix traditions that made programmability central to computing. Its terminal process model, development tools, networking heritage, and command line culture are part of why generations of engineers loved the Mac. Apple did not remove that foundation. It wrapped it inside a security architecture designed for a mass-market device carrying far more sensitive data than the workstations that inspired it. For many developers, that is progress. For others, it changes the relationship. The machine still belongs to them physically, but some of its deepest behavior is no longer theirs to redefine casually. Apple chooses which kernel mechanisms survive, which extensions are supported, which protected areas remain readable, which privileged frameworks exist, and what software must prove before Gatekeeper accepts it without friction. Linux offers the opposite discomfort. It gives the developer enough control to become responsible for choices Apple would rather make on the user's behalf. That is why the migration, where it exists, is not really about macOS becoming bad or Linux becoming easy. It is about the value of permission. As software moves deeper into cloud infrastructure, AI accelerators, security instrumentation, containers, custom kernels, and open systems, a subset of developers values the ability to inspect and change the complete stack more than they value a perfectly integrated laptop. Apple is betting that controlled power is the future of personal computing. Linux continues to bet that the owner should be able to open the machine all the way down. The hidden cost of Apple's garden is not that developers cannot build inside it. It is that the walls become most visible precisely when a developer tries to build something Apple has not already created a gate for. And that is why some of the people pushing computing closest to its limits are looking beyond the garden, not because the Mac stopped being powerful, but because power and permission are no longer the same thing.